The image stops looking random before anyone understands why. A Webb deep field fills with ancient galaxies scattered across black space. At first, the distribution looks normal. Dense regions, empty regions, irregular shapes distorted by distance. Then directional overlays appear across the frame. The lines keep matching. Several galaxy chains tilt along nearly identical angles across distances that should not share structure yet. The reconstruction gets rerun. Rotation filters change. Distortion correction strips layers from the image. The alignments survive every pass anyway. The image stops looking random before anyone understands why. A Webb deep field fills with ancient galaxies scattered across black space. At first, the distribution looks normal. Dense regions, empty regions, irregular shapes distorted by distance. Then directional overlays appear across the frame. The lines keep matching. Several galaxy chains tilt along nearly identical angles across distances that should not share structure yet. The reconstruction gets rerun. Rotation filters change. Distortion correction strips layers from the image. The alignments survive every pass anyway. The image looks wrong before anyone explains why. James Webb deep field scans from the early universe look normal at first. Thousands of ancient galaxies appear across black space, faint and warped by distance. Then researchers start drawing directional overlays across the image. The lines keep matching. Long chains of galaxies appear tilted in similar directions, as if entire regions rotated together. Not everywhere, but often enough that the pattern refuses to disappear. That should not happen this early. Less than 1 billion years after the Big Bang, the universe is supposed to look chaotic. Early galaxies should not already be lining up across enormous distances. The same sentence keeps appearing in the analysis notes. Randomness is not supposed to organize itself this neatly. At first, scientists suspect processing errors. Maybe the telescope introduced distortion during image reconstruction. Maybe the orientation software created false alignments while sharpening distant objects. Then a second Webb field reveals the same behavior. Another region, another set of ancient galaxies, another directional pattern repeating across structures separated by billions of light years. The grid overlay keeps locking onto the image. That is when observation becomes verification. The problem is no longer one corrupted-looking field. The map itself keeps organizing the wrong way, and every additional field weakens the idea that the early universe began as random chaos at all. The correction process is supposed to make patterns disappear. Engineers rotate the images, rebuild the orientation maps, strip away lens distortion. Bright objects get removed from the field one layer at a time, while the ancient background galaxies stay in place. Reprocessing the Webb fields should have weakened the pattern. Instead, the structure survives every pass. The same explanation keeps appearing in technical discussions.
We need more stability on the 9th layer.
Image correction normally destroys false organization when data is reprocessed from different angles. This one does not. The overlays still match after rotation. The directional chains survive reconstruction. Light that traveled more than 13 billion years across expanding space still arrives carrying the same directional structure. Then researchers begin comparing older sky surveys against Webb itself. Separate instruments, separate observation periods, different reconstruction systems. The galaxy maps align together anyway. That is when the explanation starts collapsing. Independent regions of the sky begin repeating similar directional behavior, as though the organization extends beyond one telescope, one software pipeline, or one section of the universe. Each verification step spreads the problem farther. Every correction meant to restore confidence now preserves the contradiction instead. And once the anomaly survives outside Webb alone, the pressure changes completely. The question is no longer whether Webb malfunctioned. The pressure comes from the possibility that it did not. A possible explanation finally begins holding the pieces together. Researchers start modeling faster dark matter growth in the early universe. Massive, invisible structures spread outward through simulation space, pulling normal matter behind them. Thin filaments connect across darkness. Dense regions collapse first. Galaxies begin forming along those hidden lanes instead of scattering randomly. For the first time, the behavior starts looking physically explainable. The cosmic web already exists today. Giant galaxy filaments stretch across enormous distances through modern space. Maybe Webb is observing an early cosmic web forming far faster than existing models predicted. The simulations expand further. Filament structures spread across the screen. Bright clusters begin locking together into connected lanes. Then the simulated maps compare against Webb imagery. For a moment, the simulated structures stop looking theoretical. The simulated map starts resembling real Webb fields. An early cosmic web, forming ahead of schedule, suddenly stops sounding absurd. Researchers begin testing whether unusually dense dark matter conditions could accelerate organization only a few 100 million years after the Big Bang. But the stability does not last. The model only works if structure formation begins almost immediately after the Big Bang. The early universe has to organize almost immediately, with structure growth pushed near the edge of the system itself. And another problem remains underneath it. If accelerated dark matter created these giant filaments early, transitional disorder should still appear somewhere between the organized regions. Instead, the maps keep arriving already structured. The explanation survives. But the numbers have to be pushed far enough that the stability no longer feels comfortable. The temporary stability breaks almost immediately. New Webb survey regions begin arriving from even deeper sections of space. Fresh overlays appear across the screen. Bright galaxy clusters stretch into repeating lanes again. Similar spacing, similar orientation. The same directional behavior repeating across distances that should not share structure yet. Deeper survey regions should have revealed something less organized between those structures. It does not. The same assumption keeps resurfacing during analysis. If giant filaments formed naturally, transitional disorder should still remain visible while the structure develops. Some regions should still look unfinished. Instead, the structures arrive already ordered. The probability curves stop lining up with the observations. Simulations generate tangled growth patterns with uneven transitional stages. Webb keeps returning cleaner geometry than the models predict. Then the side-by-side comparisons stop matching at all. Simulation outputs collapse beside Webb imagery. The explanation increases the contradiction instead of reducing it. That is when the model stops stabilizing the data. The more researchers stretch the dark matter model to reproduce the alignments, the less stable the larger cosmological picture becomes. Systems designed to restore prediction are now generating instability instead. Scientific confidence does not collapse outright. It just weakens a little more with every new field. Because the anomaly is no longer trapped inside one strange observation, the organization keeps repeating across the map itself, and the universe keeps looking structured long before the process of structure formation should even exist. The models do not recover. James Webb keeps mapping farther backward through cosmic history, deeper into light emitted before Earth existed. New regions enter the surveys, more ancient galaxies appear, long structures continue surfacing across the darkness. And the simulations keep failing in the same direction. A partially organized early universe no longer feels isolated to one region. The deeper the telescope looks, the more the structures begin resembling a faint cosmic lattice stretching across impossible distances. One assumption sits underneath the entire problem. Humans expect the universe to form gradually. Small fluctuations gradually collapse into larger structures over immense stretches of time. But here, the order appears before the process fully exists. The ancient structures keep resembling parts of a larger grid. Every stronger explanation creates new instability instead. Researchers add hidden physics, adjust dark matter behavior, push early structure formation harder and harder. The models become less reliable each time. If hidden physics forced early organization, cosmology should still predict traces of that transition somewhere inside the observations. Instead, the better Webb observes, the less complete the model appears. The direction of the problem changes there. The system is not failing through missing data. It is failing through successful observation. And gradually, the pressure changes direction entirely. The universe stops looking naturally random at all.